All right, so we are on page 25, looking at Maxwell-Boltzmann distributions. All right, so how does temperature change the speed of gas particles? That's our main question. And I'm just going to read this first little bit here. When a sample of matter is heated, the particles speed up. I think we all knew that, hopefully. But what does that mean? Are all the particles in a sample moving at the same speed? Do they all speed up equally? Does the mass of the particles affect the particle speed? Two scientists, James Maxwell and Ludwig Boltzmann, proposed an equation that could be used to predict the speeds of ideal gas particles. And if you remember, ideal gas particles, when a gas is ideal, it has to meet two criteria. And that is that the particles take up no space, which obviously is not true for anything, but the closer you can get to that, the more ideal the behavior will be. So the particles take up no space. So if you have a teeny tiny gas like helium, it's going to be closer to ideal than a large gas like methane. Okay, so helium is more ideal than methane. This is bigger. Okay, H. There we go. The second criteria is that the particles have to feel no attractive forces. There are no attractive forces between the particles. And for that one, if you had, let's say we were comparing CH4 versus H2O, I want you to think about that and decide which of those would be more ideal based on having no attraction between the particles. Take a moment and think about that. Based on the no attractive forces alone, I mean, you'd have to also take into consideration size, but if we're just looking at the attractive forces, CH4 is a nonpolar molecule, okay, because carbon and hydrogen have similar electronegativities. And also, CH4 is a symmetrical molecule. Can you remember what shape CH4 is? It is tetrahedral, yes, we would have 1 and then 2, 3, 4, a little tetrahedron here. Okay, so CH4 is nonpolar, so what is the only type of IMF in CH4? We have a nonpolar molecule. So the only type of IMF is London dispersion forces. Which, as we know, are relatively weak. Just a little review while we're here, right? All right, versus H2O, and I'm sort of running out of room. I'm running onto my graph here. H2O Now its structure looks like this. And we remember oxygen is very electronegative. So we have some serious bond dipoles, which leads us to an overall net dipole moment downward because the horizontal components cancel out. And so we have a polar molecule. So there will be London dispersion forces, simply because there's always London dispersion forces. It doesn't matter if it's polar or nonpolar. Second, there's dipole-dipole interactions. And third, because oxygen is so very electronegative, it is one of the FON and the hydrogen is attached. We also have hydrogen bonding. Hydrogen bonding is one of the strongest IMFs. So if we're like, who's more ideal based on intermolecular forces? CH4, which only has London dispersion, or water, which has like really strong hydrogen bonding, then CH4 would be more ideal because it has less intermolecular forces. So it would be closer to having no attractive forces. All right, so we have done nothing with our new topic, which is this Maxwell-Boltzmann distribution. But we have an equation based on statistics. We won't actually look at the equation, we will just look at the graph of this equation. It's based on statistics and thermodynamic relationships, and we use it to predict properties of gases such as pressure and diffusion rates and rates of reaction involving gases. And so here we have our graph, and now we're going to, this is actually a POGIL activity. So if you would prefer to do the POGIL activity on your own with a friend, rather than hanging out with me and doing it, you can choose to do that. Do you want to do it with a friend, or do you just want to hang out with me? It doesn't matter. Okay, I'm going to keep doing it because, you know, if anyone wants to just do it with me, we'll be here. Okay, but if you're like, no, I'd rather get together with a friend and do this, that is also good. I'll let you know at the end of this which page to go up to for this week. All right, so here's our graph. And our first question is, what is the variable and unit on the x-axis? So we're starting out really easy here because it's pretty obvious that the variable and unit is particle speed. In meters per second. Particles of what substance are represented on this graph? And so we go and we look and we see, it says particles of, number of particles out of 1 million. That doesn't tell me the type, but if I look up at the top, oh, it is helium. Hooray, okay. How many particles are represented in the graph? All right. It says, I'm going to give you guys a choice. You're going to tell me, is it 1 million or is it 1,000? How many particles are represented on this graph? Do you have an idea? It's okay if you don't. Not really. Okay. So this is the particles out of 1 million. So the total number of particles is 1 million, okay? It's a little bit hard to tell that from the graph, and it'll become more clear why that is as we go along. Basically, actually, I'm gonna get ahead of myself if I do this, so I'm just going to write 1 million for now. 1 million. So that's the total number of particles. And what temperatures are represented in the graph? Well, if we zoom out a little bit and we can get past all of my writing, over on the right there we have -100, 100, and 500. Okay, and I'm just going to take a moment and label those. That's -100. Oops, I should put the negative in front of that. This one here is 100 degrees Celsius, and here is 500 degrees Celsius. So we have, what was it, -100 degrees Celsius, 100 Celsius, and 500 degrees Celsius. Okay, and I'm actually going to grab Model 1 and put it next to the next bit, because I don't want to have to keep scrolling up all the time. Okay, so here we go. Well, now I'll just have to scroll to the side. Not sure that's any better, but whatever. Okay. According to Model 1, so this is our next page, according to Model 1, do all of the gas particles move at the same speed for a given temperature? So let's just look at the 100 degrees. Are all of the particles moving at the same speed? No, because otherwise we would just have like a line that was like, oh, here's all 1 million particles all going at a single speed, but we would have to go like up 1,000 times bigger than that. Okay, so no, we have particles doing different speeds all over the place. So no. If particles roll at the same speed, the graph would just be a single vertical line. Going up to 1 million. That's the total number of particles. Okay, according to Model 1, how many gas particles in the sample are traveling at 1,000 meters per second at -100 degrees Celsius? So how many are traveling at 1,000 meters per second at -100 degrees Celsius? And if we follow that up all the way to here, that looks to be about, and then we read across, I don't know, 930 maybe? 940, 920. You can choose. I'm going to go with 930, I think. Approximately 930 particles. At 100 degrees Celsius, that's this one here. Okay, so we're going to have to go up there and then read across. And I'm guessing that's maybe 620-ish. Okay, so that's 620 where we're crossing this red line here, the 100 degrees Celsius line. That's approximately 600 particles. And then finally at 500 degrees, this is this one here. Okay, so we're going to go up to there, and then we'll read across, and that looks about 300. And then I guess we get to do the same thing for 2,500 meters per second. Okay, so at 2,500, we have, oh, look, at 100, negative 100, there's essentially zero, okay? Hardly anything left. Now, technically, this is an asymptote, so you could have, like, a particle going at 1,000,000 meters per second for any of these curves, but, like, that would be, like, a really random, weird, you know, statistically insignificant. So for all intents and purposes, we are down to 0 particles. At 100 degrees Celsius, we are at about, I would say, 140, about 140. And then at 500, we would be here, and so that's going to be about 350. Explain why the 500 degrees Celsius curve is flatter in Model 1 than the 100 degrees Celsius curve. This is actually fairly difficult to explain. I really like an explanation that I have for it because it's got pictures in the next worksheet 13.3b. So we might just leave that kind of for a moment. But basically what it comes down to is that the area under the curve, well, we might as well write this. The area under the curve is equal to the total number of molecules. And in this case, that's equal to 1,000,000. If the curve gets longer, like wider, like the 500 degrees, we have it going out to ever higher temperatures. Okay, so it goes to higher temperatures. In order to have the same area, if you stretch something widthwise, you have to shrink it height-wise in order for the area to stay the same. So the (500°C) curve is wider, therefore it must be shorter to have same area as the negative 100°C curve. And since we have the same number of molecules in each, the area has to be the same for both. At what temperature are the helium particles in the sample moving the slowest? on average. Okay, I'm going to go over here and I'm going to erase all the nonsense that I've drawn on here so you can see the curves again. At what temperature, on average, are the helium molecules moving the slowest? Then -100, okay? That's pretty straightforward because, you know, you've got a peak here, yes, and then as we get to higher temperatures, our peak moves to higher and higher speeds. Okay, so that would be -100 degrees Celsius. At which are they moving the fastest? That would be at 500 degrees Celsius. When a sample of gaseous matter is heated, do all of the particles in the sample speed up? Well, on average, they speed up, but we still have some particles, you know, that are moving at 500 meters per second, regardless of what temperature we're at. So on average, they speed up, but not necessarily every single particle speeds up. In fact, you could have one particle that was going quite quickly, and if it happens to collide in a particular way with some other particles, it might end up going slower than before, even at a higher temperature, just as long as, on average, all the particles are moving faster. All right, let's see. Circle the set of drawings below that more accurately illustrates the difference in particle speeds at 100 degrees and 500 degrees. Hint, the longer the arrow, the faster the particle is moving. All right, so let's take a look at these. So at 100 degrees, what would it mean that all these arrows are the same length? That would mean that all the particles are moving at the same speed. Is that true? No. And then same thing for the one at 500. Ditto. Okay, same here. So it is better to have, on average, the arrows are longer. Therefore, the speed is greater. But we have a variety of speeds. And also here we have a variety of speeds. So the answer is, this one is our happy answer. And you know what? I predicted we were going to get to question 9. And it is like 1 minute before 9, and we got to question 9. Hooray! Okay, so we will continue on with this next week. Like I said, though, if you'd prefer to have, well, I guess if you got to this point in the video, you've been watching along with me and won't be doing it with a friend, but oh well.